This is the final video discussing Maxwell's equations in different representations. We started with the vector form of Maxwell's equations in matter. We restricted those to linear isotropic media, where we have a linear relationship between our D and E field and our B and H field. Then we formulated the Euclidean basis geometric algebra form of Maxwell's equation. Then we go to space-time algebra, also in geometric algebra, and formulate the space-time algebra STA form of Maxwell's equation, which is just grad f equals j, where grad is a space-time gradient. F is our electromagnetic field, and j is our current and charge density contribution. From there, we went to the tensor algebra form of Maxwell's equation, which has this particular structure. And for this final video, we're going to show what the differential forms representation of starting from the STA form of Maxwell's equation. So our STA form of Maxwell's equation is grad f equals j. And just to summarize, grad is a differential operator. And f is a bivector. So your f mu nu in this case is a completely antisymmetric tensor, and we basically have one bivector term for each mu nu combination that's unique. So 0, 1, 1, 2, 2, 3, 1, 3, and so forth. I missed 0, 2, 0, 3, I think. Anyway, so we have 6 bivectors in space-time algebra, and our electromagnetic field has one of each term plus a coefficient. And our j, we wrote as j mu gamma mu, where j0 was eta c rho, or rho over epsilon, and jk was eta vector j dotted with ek. And eta, for reference, was square root of mu over epsilon, and c, which is in here implicitly, c was root of mu epsilon, and mu is not in the picture in this representation. Anyways, this was the space-time algebra form of Maxwell's equation. Now we're going to go to differential forms. So differential forms, we're going to start with grad f is grad dot f plus grad wedge f equals j. Now, f is bivector, space-time gradient is a vector, bivector, vector. So this is a vector, the dot product, and our wedge product is a trivector. And here on the other side, we have a vector. So with two equations, we can split this into one equation for each grade. So it's grad dot f equals j, and grad wedge f equals 0. Once split like this, which we did the same split for the tensor algebra formulation, we can rewrite grad wedge f equals 0 as a differential forms operation. We can actually just write that down almost immediately. So if we write f, that is d mu wedge d mu. I think I used indices downstairs before, and now I'm putting them upstairs, but it doesn't matter because they're matched with f mu nu. So if I do a lowering operation on this mu, I do a raising operation on this mu, and everything works out. Same deal for the new indices. And we can, right away, just write this as a differential form. dx mu, dx nu, f mu nu. So here is our representation of our electromagnetic field in differential forms. We just take our reciprocal frame vectors and translate those into differentials. And remember that in differential forms, dx mu, dx nu is implicitly dx mu wedged with dx nu. The product of differentials builds in the antisymmetry of a wedge product. This is not the wedge product of vectors in this case, this is the wedge product of one forms. So we construct a two form by multiplying two one forms. And the multiplication of one forms is through the wedge product. This is the one form, one form. So now that we have a representation of our electromagnetic field as a two form, we can just write down that d f equals 0. That is the isomorphism of grad wedge f equals 0. So in STA, everything is a vector or a bivector, and we translate that into a three-form equation, df equals 0. And the d, if you recall the f, what this really means is it means we have df dx mu, dx mu, let's be careful with orders, is dx mu wedged with df. So the antisymmetry of the d operator, antisymmetry of the d operator is the direct representation of the curl and that we have in an equation like grad f equals 0. So there's one of our equations in differential forms. For the other equation, we have a little bit more trouble because how do we represent grad dot f equals j? So here we have a vector, 4 vector, we have bivector, and a vector. So grade 1, grade 2, grade 1, we don't have anything like a grad dot operation in differential forms. So how do we represent this equation? The way we can do this, a little bit sneaky, is we start back at grad f equals j. Now we multiply everything through by the pseudoscalar. This is a duality transformation. Remember, in differential forms, we have a duality transformation that we represent as star a. If a is let's say one form, then star a might be a n minus one form. In our case, we have 4. So if we had a vector, then star a would be a 3 form. So we're going to apply a duality transformation to both sides. So we're going to end up with, now we have grade 3, and we have a multivector here. But grade 3 is going to have the isomorphism to a 3 form that we want. So we can rewrite this. Remember that the STA pseudoscalar anti-commutes with vectors. And that's a consequence of it having 4 terms. And so for each element in the pseudoscalar that you try to commute with, you get a sign change. You end up with an odd number of sign changes, 3. So we can rewrite this as minus grad IF or grad minus IF. And in particular, we can now decompose this and note that, so we have a bivector and a pseudoscalar, so the whole thing together is still a bivector. So we can say grad dotted with minus IF plus grad wedged with minus IF equals IJ. So this is now grade 1, this is grade 3, and this is grade 3. So we're going to equate our grade 3 components and equate the grade 1 component with 0. So we've found a way to rewrite Maxwell's equation as as a vector, 0, and as a trivector, now in this form, is that correct? Yeah, it must be. Okay. So now, this is, if we say what is I minus IF and what is IJ, minus IF is minus I times E plus ICB is minus IE plus CB. These vectors. And we can write this out in component form, which is going to be C, BK, gamma K, gamma naught, plus gamma 1, gamma 2, E3, plus gamma 2, 3, E1, plus gamma 3, 1, E2. And we'll just switch to the reciprocal frame. So we have C, BK, minus CBK, gamma K, gamma naught, plus gamma 1, 2, 3, and so forth. So now we can translate this into the differential forms. By inspection, we now have dx1, dx2, e3 plus dx2, dx3, e1 plus dx2, 3 dx1, e2 minus c ek dx k dx0. There we go. Here is our minus I f, which we're going to call star f as the dual of f. So we have a representation of this. It's an ugly little beastie. We could probably write that out in a tidier way, but that's good enough. And then we have an ij term as well that we want to have a differential forms representation of. And ij is going to be gamma naught 1, 2, 3, gamma u, j u, or let's write that as gamma minus gamma 0, 1, 2, 3, gamma u, j mu. That's better. So that is now minus gamma 0, 1, 2, j 3 plus gamma 0. So if mu is 2, then commute with gamma 3, flips the sign, then I have the gamma 2's obliterate, and I'm left with 0, 1, 3. 0, 1, 3, J2. I'm going to minus sign for the next term, which would be 0, 2, 3, J1 plus gamma 1, 2, 3, J0. So there is our representation of J in the differential forms. And really, I think that this would actually be star of dx mu j mu. If you were to figure out how to do that in differential forms, and I don't know differential forms well enough to verify that's the case, but I believe, oh, this is slightly premature actually. I haven't actually written out. So now we have a correspondence between ij in differential forms that is going to be minus d x naught dx 1 dx 2 j 3 plus dx 0 dx 1 dx 3 j2 and so forth. You notice that we have here 0, 1, 2, 3. Here we have an odd permutation of 0, 1, 2, 3, so the sign is flipped. So we're just going to do all the permutations of dx a, b, c, d, or alpha, beta, mu, nu, that have and then all of those permutations of 0, 1, 2, 3, 4, that, and then with a negation in the front. So when we're done, we're now left with df equals 0 and d star f equals j. There's our differential forms. And I think that the tidiest way to write this would be f equals 1/2 of dx mu dx nu f mu nu, and this is going to essentially be the equivalent of the Hodge dual. This is going to be the equivalent of the Hodge dual, whereas this is a 3-form equivalent, should be the equivalent of the dual of, let's write a small j, let's write j equals dx mu j mu, and we'll say that j as a 3-form is star j. There is our entire Maxwell's equations in differential forms. Like the tensor relationship, it's fairly compact. Not as compact as the STA relationship, and I'm not actually as familiar with the differential forms representation. I don't know how you would do much with it, but I'm assuming that somebody who knows it does know that, knows how to apply Stokes' theorem and so forth in its differential forms representation. You could probably compute some interesting things. I don't know how you would attack this with Green's functions like you can in geometric algebra, and that is also an exercise for somebody else who knows differential forms representation better than I do. Which is probably almost anybody. Anyways, that's the end of the series. I hope it's been of interest to anybody who wants to know some of the different possible representations of Maxwell's equations. And we've seen the vector form of Maxwell's equations, the geometric algebra form of Maxwell's equations with the Euclidean basis. We've seen the geometric algebra form of Maxwell's equations with a manifest relativistic basis, the Dirac basis, and we've seen the form of Maxwell's equations in in their coordinate form, where we take the STA form and write out its coordinates. That's a tensor representation. And we've seen now finally the representation of Maxwell's equations in differential forms notation. All of these are equivalent, and you should be able to work from any one to any other if you had the need to. And I've worked through geometric algebra as an intermediate for all of the different representations, primarily because the geometric algebra form is the most compact of them all, so it's the easiest to get from that form to any other representation. But if you wanted to, you should be able to get from the tensor form to the vector form, or vice versa. That is the end of this series.